Great, here we go. Okay, now we're getting into chapter 6 for sensors. Book review. Chapter 6 is where it's at, guys. This is a good chapter. It talks about thermocouples, and obviously the hot junction is the part that you're measuring. Even if it's not hot, it might be cold. And the cold junction is the part where you've connected up to your voltmeter or your instrument, right? So those are the two key things about thermocouples. So you have to know what the hot junction and the cold junction are, okay? Those are critical. Cold junction, what you wire into your device. Hot junction, where your temperature measurement is, even if it's not hot. You have to understand what the Seebeck effect is. That's this whole idea that dissimilar conductive materials um, and electricity that flows based on those dissimilar materials changing in temperature. We have a few more effects as well that come into play. You have the Peltier effect, which is kind of the opposite of the Seebeck effect. Heating and cooling occurs at the junctions of two dissimilar materials when a current flows. So if I actually used a battery on a thermocouple, I can turn it into a heating or cooling device, which is kind of cool. All right. We also have the Thomson effect. Heat is generated or absorbed when an electric current passes through a conductor, right? So I can actually heat or cool something depending on which direction I flow energy through different kinds of materials. So it's usually very, very slight, but it's really, really kind of an interesting effect. So in the end effect, the voltage that produces the Seebeck current is the sum of the Peltier effect voltage and the two Thomson effect voltages along the dissimilar wires. So you really have to account for all of them. Now, luckily, the Peltier effect is the largest effect, and all this complication of effects can be wrapped up into one lookup table for each RTD, for each thermocouple type. So that one lookup table or the computerized thermocouple device for measuring thermocouples can automatically do all this fancy math for you. You don't need to know how it actually works on the inside, though it is useful to understand that they have all these magical effects of dissimilar metals that's going on. The book actually does a great job talking about hot and cold junctions. And there's a few different laws associated with the kind of metals you would use in these junctions. And I'm going to kind of soft shoe this whole section a little bit. These are all interesting concepts. But the bottom line is when you wire up thermocouples, you have to follow the recommendations of the manufacturers in how you hook those thermocouples up. In many cases, you're going to have a special kind of connector that you would use. You always want to use the connector they offer. The only time you're really going to have to worry about weird thermocouple hookups is when you're doing calibration. When you're doing calibration, you might hook up something like this, where your hot junction is whatever your heat source is or your temperature that you're measuring is, but your cold junction, the place where you hook the thermocouple wires to your copper wires, is in a temperature controlled device like an ice bath. So you will see this if you need a very accurate thermocouple measurement. For the most part, though, you're going to get this, a regular old thermocouple circuit where your copper wires are hooked to your dissimilar wires on your thermocouple wire, and hopefully they're in the same area. There's no temper differential, so you don't lose accuracy that way. And that would be this case where we now have a isothermic block that is exactly the same temperature is true between both junctions, between copper and thermocouple wire. So you're going to read a little about thermocouple construction. This book doesn't really go into a lot of detail. It's very common to see thermocouples that vary substantially. I'm going to bring a couple thermocouples in with me into class, and we're going to look at a couple of major different thermocouple types, including some very high temperature thermocouples with these insulating beads on them. And thermal wells, we're going to talk about what a thermal well is and how it functions, protects the thermocouple, kind of gives it a little place to hide it from the damages from your process. So I'm kind of soft shoeing the rest of this chapter because you generally have electronic devices that will do your thermocouple analysis for you. You don't need to pull out a voltmeter anymore. You don't need to do interpolations much anymore. Thermocouples are, you can use a voltmeter on it, but the numbers bounce around. You create inaccuracies based on the connection to your voltmeter leads. You can do that, but it's much better just to use another device that's going to give you an accurate thermocouple reading. Page 56, very important page. That's your quick lookup location in the book for your thermocouple wire types, wire colors. Focus on US and Canada, right? There's a whole bunch of other nationalities out there with thermocouples, but 90% of what you're going to find in the US is US and Canada thermocouple wires. The book does a really good job of describing some of the problems with different thermocouple types to help you choose among them. Chances are, as technicians, you're not going to have a choice. You're going to get whatever thermocouple came with that machine or came and was specified by your engineer. But just read about the different types. For instance, anything with iron in it, the iron can rust and oxidate. That's a problem, lose accuracy. K-type thermocouples have something they call green rot, of all things. The alloy turns green because of oxidation. That's the chromo wire. Becomes magnetic. All right. Sheath thermocouple construction is the most common. Most often you're going to see a stainless steel tubing used as shielding. And here they mention being packed with magnesium oxide powder. Why do they pack with that powder? Because it's non-conductive and provides you good temperature. I mean, it's not electrical conductive, but it is great temperature conductor. And there's just a couple little notes on that. A thermopile is multiple thermocouples, and there's a special way of wiring them up to get a very accurate measurement. Averaging thermocouples, we take two and we average them. That improves your accuracy overall. The more you average, the better. Pyrometers are ability to see very high temperature devices, and you can read about them. All right, but we're going to jump through most of that. We're going to jump right into RTDs. Resistance temperature detectors. Resistance temperature detector, RTD. These are tiny little coils. They use different electronics to measure them. Instead of measuring voltage like you would with a thermocouple, you're measuring resistance, R. And if that resistance has a standard drop across at each temperature that it's in, and it has only a slight change. So you need a really, really accurate way of measuring resistance on these devices. And the book shows you, well, inside here, you can see an RTD wire inside of a sheath. You just see that copper sheath, so it's not super useful. Inside there is a tiny little coil. Here they show you an RTD coil wrapped around an insulator inside the protective sheath. That's actually not a great diagram as well. And actually RTD coils are very tight, thin, and round, usually not square like that. Platinum wire is your best material for RTD. Platinum is expensive, therefore RTDs are expensive, but they are very accurate. So read about RTDs. Thermistors tend to be a lot more expensive, temperature sensitive, resistor made of solid state semiconductors. So a thermistor is like an RTD, but it's using a semiconductor material to create it. They can be set up for very specific temperature ranges. And read about PTC resistant thermistors. They're very interesting. The last category, only briefly mentioned, but growing hugely in popularity, are semiconductor thermometers. Any device that has a built-in thermometer chip, like all sorts of small computer systems do, uses semiconductor thermometers. They tend to be inaccurate, but they allow for very, very cheap methods of measuring temperature in the range of, 30 cents per sensor if you build it into your board. So this is a growing area of expertise.